Okay, let's look at the topic of verifying independence. Again, it may be a little bit cumbersome or tough to check all the sets and see, okay, do I have factorizations of all the sets in the world? So that's why we might think of, is there a more convenient way? And yes, there is. So this is proposition 5.5 in the lecture notes. So I have a theorem here for you. And what does it say? It says that let's assume that we have I1 and I2. We assume that they are generating pi systems for sigma algebras G1 and G2. If this is the case, then to check if the sigma algebras G1 and G2 are independent is equivalent to checking that we have this factorization, that there are factorization for all the members of the pi system. So for all I1 in the pi system I1 and all I2 in the pi system I2. This is the proposition. So again, it says that, okay, you don't need to go all the sets in the world, all the measurable sets in the world. It's sufficient to look at the generating pi systems and verify things that they work fine over there. This proof is my favorite proofs in probability theory because it's really illustrating you lots of things and kind of many things kind of fit into place. So I would be happy to discuss a little bit about this. So this proof works in two phases. First, in phase one, we fix one I1, which is a member of this I1, and then we claim that our first claim is that we have factorization, that probability of I1, and any event E2 factorizes using I1 and E2. And we claim that this is true for all E2 in G2. What does it actually mean? It's kind of a bootstrapping thing. Remember the story about bootstrapping, that the story is that there was a baron who tried to lift himself out of the swamp by lifting from his own boots. Okay, so in this sense, we bootstrap. So now we know that we have a property. This is our property here. And we kind of want to lift this property from the pi systems to the full sigma algebra. So we want to kind of lift ourselves out from the swamp to kind of a nice domain. So what this part one is doing, that, okay, we say that, okay, I1 is one boot still in the swamp. And then now we fix the left foot in the swamp and we try to lift our right foot to the full domain, so the G2. And let's see how to do this first kind of bootstrap phase. And we assume that the probability of I1 is not 0. Why not? Why do we do this assumption? If probability of I2 would be 0, so then we would have 0 here on the right. This would be a subset of something with probability 0, so then we would have a probability 0 on the left also. And so that this claim would be trivial. This claim here, this claim that we look at here would be trivial if probability of I1 would be 0. So that's why we assume that probability of I1 is non-zero, or we could say it's strictly positive. Yeah. Then what can we do? Let's look at conditional probabilities. So let's calculate what is the conditional probability, and let's use a special name for it now. Let's define P tilde E2, P tilde 2 of E2. And let's define this to be the conditional probability of E2 given I1. And this notation is shorthand for the usual thing. So it's shorthand for I1 and E2 divided by the probability of I1. So that's the conditioning event, and we can now divide because this is non-zero. This is the first time that we see this notation, but now it's defined with this. This is the definition of that notation, and this is the definition of the P tilde 2. Okay. Then what? Then actually we note, and we define this for every E2 in G2. Then we know that actually this map from E2 to P tilde 2 of E2, I think this was in your homework, so this is a probability measure actually. We know that conditional probabilities are also probability measures, and this is a probability measure on omega and G2. Okay. What do we know about this probability measure? We know that if we pick something in the swamp, let's say, we pick I2 now, they're in the pi system. So then if we calculate what is P tilde 2 for something in the pi system, by definition, it is the product of I1, I2, and then we divide by the probability of I1. So it's the probability of this intersection divided by here. And now, what do we know? We assume that we have this condition true when everything is in the pi system. So now we are using the assumption. So, okay, let me remind that again, this direction of the proof is trivial because it's directly from the definition. That's why we are not proving that at all. We are proving the reverse direction. So we assume that this condition is true, and we want to prove independence of G1 and G2 sigma algebras. So when we want to prove the reverse implication, so we are proving this one only, the non-trivial part. So now from the assumption red star, we know that this probability factorizes nicely. It factorizes here above. And then we can divide these away and we get probability of I2. Yep. So we see that this P tilde 2, this is a probability measure. And then here we have P. So we see that they agree on I2. Yeah, we have two probability measures. They agree on a pi system I2 because for every member of I2, this tilde gives the same as the standard probability. We use Denking's identification theorem. Which says that, let's recall it, if two probability measures agree on a pi system, then they agree everywhere. That's the Denking's theorem for identification of measures. So then we conclude that actually P tilde 2 and I and P, they agree on the full sigma algebra generated by I2, which is by the assumption it is G2. And therefore, because they agree on the full G2, now we can compute P tilde for any set in G2, and we know that this is the, by definition, it's the I1 E2 divided by the probability of I1. And now we know that it agrees. Let's maybe write it in the other side. So we know that the standard probability of event E2 is equal to the P tilde of 2, and it is this one here. And now if we multiply both sides by the probability of I2, it follows that probability of I1, probability of E2, this product is equal to the probability of the intersection. And this is true now for all E2 being in the sigma algebra. And now let's look what have we done actually with all of this. We did assume that we fixed one set in the pi system 1, and then we were able to prove that actually we can lift our right foot from the swamp, and we can actually extend this property star, which was only true for the pi systems. Now we actually can replace the second member by a general member of the sigma algebra. And that's what we did here. And the trick was to kind of transform things into measures, think about conditional probabilities, and use Dinking's identification theorem. Okay. What remains is part 2. And what we should do there is actually, it's a very similar thing. So in that case, we now fix a second member, but now we fix it in the sigma algebra. So now we kind of fix our right foot in already out of the swamp, and then we kind of what we want to do, we want to lift our left foot in this way, and kind of we do the same trick again. It is a very similar thing to do again, and it works. If you want to be convinced, I recommend you can read it in the lecture notes how to repeat the same trick again when now the E2 has been lifted already to the sigma algebra. This is the proof of the proposition 5.5 for verifying only things in the pi system. Do you have questions about this part? If not, let's do one more thing and as an example how to apply this result. So let's do a corollary. That's called corollary 5.6 in the lecture notes. And what does that one say? It says that for two random variables, they are independent if and only if, let's say for x1, x2 now being random variables on the real line. So in this corollary, we look at two random variables on the real line. And what does the corollary say? It says that these are independent if and only if we have this type of factorization, that the probability of x1 less than little x1 and the probability that x2 is less than or equal to little x2 factorizes. How to do this and how to prove it using the theorem, the proposition that we proved. We can define we can define J to be the collection of these intervals with x being a real number. We can define I1 to be the pre-images of these intervals by x1. And we define I2 to be the pre-images by x2. So we take the pre-image by x2 of the J. Okay. So then you can check, I leave it up to you, that I1, I2 are pi systems. And we also know that what does the I1 generate? It generates the sigma algebra generated by x1. So it is actually I1 generates the sigma algebra of x1. And similarly, I2 generates the sigma algebra of x2. This is done in the lecture notes, you can check. And then we know that for if we now test, we pick any members from collection I1 and another member from collection I2, then what? Then we know that I1 is of the form the set of omega for which x1 omega is at most x1, and then this is similar pre-image for some other x2. And that's why the probability of I1 in the section I2 factorizes, because that was the assumption. For all I1 being in collection I1, for all I2 being a member of collection I2. And now we have the factorization for pi systems, and then they generate these sigma algebras. So that's the corollary we get now from the proposition. Let's open it again. So for real valued random numbers, x1, x2, checking independence can be done using the kind of joint cumulative distribution function here. Does it factorize in this product? This is actually kind of the starting point for a theory called copula theory, which was popular in insurance mathematics. So understanding and trying to quantify dependence using functions on the unit square and so-called copulas. All right.